Hello and welcome again to our journey into number theory, and we've been looking in this chapter at the Riemann zeta function, and of course we're aiming to be able to extend the Riemann zeta function to the whole of the complex plane, and we're going to do that by developing the functional equation. Now that all depends on this result we proved in the end of the last section, which gives us a lovely connection between the zeta function and the gamma function in terms of an integral. You might like to just stand back and just enjoy, in some sense, the philosophy here that we're starting off with a function that really gives us information about prime numbers. We've got gamma, which really is a extrapolation of the factorial function, and the two are related together almost mysteriously by this rather strange looking integral. Now, in order to get the function to the functional equation, we have to step fairly gently, because one always has to be very careful about making sure that things converge and things make sense as we go. So it's a lot of very careful. It's like walking on eggshells to some extent, as you'll see as we go through it very carefully, step by step. And it's slightly technical, but this is what Riemann did, and it's a nice derivation of the functional equation. So our aim then is to extend the definition of zeta to include, firstly, the region -1 is less than the real part of s is less than 0. Now we proceed by, we're going to be using that integral that I just showed you, and so I'm going to look at this term in the integral, 1 over e to the t minus 1, and it's easy to show that that has a simple pole when t is 0, and you can get the residue as being 1 using, and then, so that means then that 1 over e to the t minus 1 over t, so it's a simple pole, so I take a 1 over t, and the residue is 1. So if I subtract that principal part of this function, then I should get an analytic function. I'd like to know what the constant term is, and so I can use L'Hopital's rule to show that that actually tends to a half as t goes to 0. That means then we can write down a Laurent series for this function, 1 over e to the t minus 1. There's the principal part, simple pole residue 1, there's the constant term, and then I'm going to get the rest of the series, which is the sum, I'm going to call it a sub nt to the n for t not 0. So this is essentially, if I think of t as complex, then this is really just the Laurent series for this function. Now it's left as an exercise to show that the even terms of this, the even coefficients of this, are all 0. That's actually a nice exercise and very easy to do. You simply show that this minus this plus this is an odd function, and so it can't have any even powers there. So thus far all we've done is we've now shown that if you take this 1 over e to the t minus 1 minus its principal part, then this is analytic, and this expression here for the real part of s, this thing here is an analytic function of s for the real part of s bigger than 0. So it's analytic, and for the real part of s bigger than 1, I'm going to write this term here. I'm going to write the integral of t to the s minus 2, which is what I get when I multiply these terms out. That's equal to 1 over s minus 1. So I now take my product formula that we had before, this formula relating zeta and gamma, and I'm going to split the integral up into the integral 0 to 1 and 1 to infinity. Because I've got problems at both ends. I've got problems at 0 and problems at infinity, so I split it up into 2 bits. I can then, in the first integral then, I can replace the integrand by this. Now what have I done? Well, I've subtracted off 1 over t times this, But that integral we saw above was just 1 over s minus 1, so I add it back in again. And then I've still got this integral here. And once again, we can now extend the definition of zeta now using this formula from the real part of s bigger than 1. This gives us yet another analytic continuation, giving the same values, of course, because they're unique, to the real part of s bigger than 0. I'm now going to suppose that my s, the real part of s, the sigma, is between 0 and 1. In that case, I can write this term, which is this one up here, I can write that one as an improper integral as minus integral 1 to infinity t to the s minus 2, and I use that to pull this term into the second integral. And then having done that, I can then combine them together, and I can now write my product, gamma s times zeta of s, now as this expression. So we'll keep that one in mind, and that now makes sense for the real part of s between 0 and 1. Now I do exactly the same thing. I repeat the argument this time. I'm going to now, instead of using just the integral, or this integral that we had before, I'm now going to use this integral and split it up in the same way as we did in the earlier section up here. So, just line this up here. So that means I can now write this integral. I'm going to split this as we did before into the integral from 0 to 1 and the integral from 1 to infinity. And again, I'm going to add now in this half times this one, and then I have to subtract its value. And I get this one here. Now, both of these integrals now are convergent for the real part of s between minus 1 and 1. We can now push the boundary even further. Both of these converge for real part of s between minus 1 and 0. And if I divide by gamma s here, then I get 1 over 2s gamma s. But 1 over s gamma s is 1 over gamma s plus 1 by that reduction formula for the gamma function. And that one now is analytic at 0. Because remember, gamma of s was analytic for s bigger than 1, so gamma s plus 1 is now analytic for s bigger than 0. Sorry, there's 0. Consequently, we can extend zeta of s to a meromorphic function defined on the real part of s bigger than minus 1. Now, we're going to try and push this term into the second integral here, as we did before. So for minus 1, for the real part of s between minus 1 and 0, this minus 1 on s can be written as the integral 1 to infinity of t to the s minus 1. So once again, I can push this term into the second integral, and that gets me this expression here. So I've got another way now of writing this product, and this is valid for minus 1 less real part of s less than 0. Now, we take a slightly different tack at this point, so we're going to now just either recall this this integral here, pi cot pi z, which is 1 over z times this sum. Now this is a standard result which is obtained using residues. You can do it as a tutorial exercise, or you can also do this by using the following. For those who want to play with this and get this out directly, if you take the well-known product for sine of x, you may have seen this product in courses in complex analysis or in some real analysis courses, you can write the sine of x as an infinite product. So it's the product of x times 1 minus x squared on n squared pi squared. And if you take the logarithmic derivative of this, then you'll obtain this fairly easily. So you can get this result out by just taking the logarithmic derivative of the product formula, the well-known product formula for sine of x. So I'll leave you to do that, or look up the formula in a book, or use complex analysis to rederive it. But I'm going to be using this formula here, and so I can change variable here and write this as cot z, as I had on the other page, is 1 on z plus this sum. Now the reason we're going to need that is I'm going to take this 1 over e to the t minus 1 minus 1 over t plus a half, and I'm going to combine this term with this term, put these over a common denominator, which gives me this expression. And this one here, of course, you may recognize, you can write this in terms of cots. So I can write this as I on 2 cot it on 2. And then the minus 1 on t copies down. And so I wanted a nice formula for the cot. So I can now substitute in the formula we had up here for cot. I can plug that in, and I'm replacing z with it on 2. So 1 over z gives me 2 over it. Now this bit happily is going to cancel. This one we copied down from above, but this one's going to simplify to 1 over t and cancel out. There's the series for cot that I just plug in. And when the dust settles on that after you've simplified it, you get this expression here. So that enables us then to write the integrand of our product formula above using this infinite sum. So for the real part of s between minus 1 and 0, I can plug that into the formula we had above, and I can write the zeta of s times gamma of s is just twice this integral times t to the s dt. I'm just plugging that in, and I simplify. In this stage I'm going to use again dominated convergence theorem that I mentioned in the previous section. I can interchange the sum and integral, and that's justified by dominated convergence theorem, to give me this expression. Now I want to get rid of this, these pi's and 4's and n's and things, so I'm going to make a change of variable here and write t is 2 pi n u. That'll have the effect of turning that into a 1. So when I plug that all through, I get this expression here. After I substitute it, you can check the various steps. And I can then split this, take all the terms that are independent of u out, and I get this expression here times this integral. Again, simplify this, lands me back to here. Now at this stage we're getting slightly more excited because this looks like the zeta function, except instead of s we've got 1 minus s, which is going to give me some sort of functional equation, and that's what I'm doing here. So I can replace this sum now with zeta of 1 minus s times this integral. Now again, we look at the case when s is real, and x between 0 and 1. And again, we'd like to know what this integral is, and one again from complex analysis, and it's an exercise to show that this integral here is equal to pi on 2 sec pi s on 2. Again, if you've done courses in complex analysis, you'll know how to deal with these real integrals by taking them into the complex plane and then doing some contour integration, use residues, and then this comes out. It takes a bit of work, but you'll find this in any standard book on complex analysis. Finally then, I can substitute that in place of the integral, and so I get zeta of x, at the moment gamma of x, is this expression we had before, zeta of 1 minus x, and I can replace the integral by pi on 2 cos pi x on 2. Well, we can use the double angle formula very cleverly here and replace this cos with a sine pi x on 2 over sine pi x. Why do we do that for? Well, because we know that there's some connection between pi on sine pi x and the gamma function from that functional equation for the gamma function, so that's a sensible thing to do. So I'm just using the double angle formula from high school trigonometry. Finally then, when the dust settles on that, I can replace this pi on sine pi x by gamma x gamma 1 minus x by the functional equation. And for the final step, we're going to divide by gamma, both sides by gamma of x, and behold, we have the so-called functional equation of Riemann. This was the functional equation for Riemann, and this will be true by analytic continuation. Now just enjoy the formula and try and ignore some of the, try and see the wood for the trees here with this. This connects zeta of s with zeta of 1 minus s, with some various other factors here. The key thing is zeta of s and zeta 1 minus s. In other words, if we think of this in the complex plane, then this is 1 here. This is giving me, telling me how to calculate something over here by simply taking it symmetrically about this. So I can connect zeta of s with zeta of 1 minus s. So this enables me to move from one side of this line, real part of s is 1, from over here. It enables me to find value or define values of zeta for values over here on the other side. So this is the so-called functional equation, and it's quite central to any study of the Riemann zeta function. And we will look at this again. This formula looks, the functional equation looks very odd and very strange, but Riemann found a way of relabeling things, rewriting things in here to make it a lot more transparent, as we'll see later. So we do just a little bit of couple of points here to note. So we've established the functional equation for minus 1 less than real part of s less than 0. Now the right hand side is defined an analytic provided 1 minus s is not 0 minus 1 minus 2, because these are the singularities of the gamma function. The real part of 1 minus s is bigger than minus 1, since this is the domain of zeta at this point, and provided 1 minus s is not 1, which is the singularity. So it is analytic provided the real part of s is less than 2 and s is not 0 or 1, and thus both sides are analytic for the real part of s between minus 1 and 1, except at 0 at the moment. Thus this gives an analytic continuation of zeta to the whole of the complex plane, with only a simple pole at s equals 1, as we've seen before. So just as a little calculation, I note here that zeta of minus 1 is equal to minus 1/12, and zeta of minus 2 is 0, and in fact zeta is 0 whenever we have a negative integer, and that's because of the sine term. Whenever we have s is a negative integer, I'm going to get sine of pi terms coming into here in the formula, and that'll make the thing 0. Now, just to show you why zeta of minus 1 is minus 1/12, which is a kind of famous formula that Euler played around with, sort of semi-jokingly, I think, but this is an interesting little thing here. So I'm going to use the functional equation. So to get zeta of minus 1, I just put s as minus 1 in. So I get 2 times 2 pi to the minus 2, gamma of 2, zeta of 2. So 1 minus minus 1 is 2. And that's where these 2's are coming from. And then I get sine of minus pi on 2. Putting s to be minus 1. And the point is we can calculate these things. This is just 2 on 4 pi squared. Gamma of 1 is 1, factorial is 1. Zeta of 2 is pi squared on 6. And the sine of minus pi on 2 is minus 1. And that collapses down to minus a 12th. Which leads people to write down funny things. If you think about what zeta of minus 1 looks like as a series, so I'll put this in inverted commas, then this is 1 over 1 to the minus 1 is 1, plus 1 over 2 to the minus 2 is 2, plus 3, plus forever. And according to this should be minus a 12th, which is one of those funny, silly formulae that people sometimes write down in the context of this. It's really not quite what it seems. It's simply saying that the value of zeta of this extended analytic continuation of zeta at minus 1 is minus a 12th, but symbolically, in some funny sense, this has some truth to it, and it's one of the formulae that I think Euler was aware of, and he wrote down, one wonders, with a certain amount of tongue-in-cheek. Finally then, to find zeta of 0, which we haven't done yet, so to find zeta of 0, again I'm going to use the functional equation. So zeta of 0 then, I'm going to do it as a limit, so I'm going to take the limit as s goes to 0 from above of zeta of s, and using the functional equation. So I just write down again our functional equation. Now as s goes to 0, then this is going to go to 1 on pi. The gamma of 1 is 1. I'm going to get zeta of s minus 1, and then sine. So this is still the limit as s goes to 0. So as s goes to 0, gamma of 1 minus s goes to 1. And this thing goes to 1 on pi, which is just a constant. So I've still got this product here. Now the problem with this, as this goes to 0, then this is going to infinity and this is going to 0. So all I'm going to do here is I'm going to use the series expansions of these. So zeta of 1 minus s is just minus 1 on s plus some function of 1 minus s, where this is bounded as s goes to 1. And I take the series for pi s on 2, take its first couple of terms of its Taylor series, so it's pi s on 2 plus big O s cubed. And when the dust settles on that, this one is, so zeta of s is equal to this, where this is bounded. And as s goes to 0, when you expand this out, you're going to get a pi on 2 there, a minus pi on 2 times 1 over pi, which is minus a half, and all the other terms will go to 0 as s goes to 1 from above. And so there's the value of zeta of 0. Now in the next section we're going to be looking at the question of what are the zeros of zeta of s? Can we find where this is 0? And of course that will lead us immediately into the famous Riemann hypothesis.